So in this video, we're going to address how our convolution integral is relevant to our Laplace analysis. But before we do that, we want to simplify that convolution integral by making a couple assumptions. So we're going to aim to simplify our convolution integral with a couple assumptions. And we're not going to go into too much detail describing why these assumptions are accurate, but of course if you were to study more in a sort of traditional signals and systems, we could see that in most cases these are going to be accurate assumptions. So we can assume that our x of t, our input, is going to be 0 for t less than 0. So for time before 0 we have no input, and so what this does is it's going to change the lower limit of our integral to 0. So it's going to go from negative infinity to 0. Another assumption that we can make is that our impulse response, h of t, is also equal to 0 for t less than 0. And so this is going to affect our upper limit, but another way that we can sort of say this is using some jargon from signals and systems, is we can say that our system is causal. And so, as I said, this is going to change our upper limit from infinity to t. So the upper limit on our integral will just be t. So we can rewrite our expression then as the output y of t is equal to x of t convolved with h of t, which is equal to the integral. So now our limits are 0 to t of x of lambda times h of t minus lambda d lambda. And so this is the analytical expression we would use to evaluate convolution if we have our functions of t and they're nice and discrete and we can evaluate this integral. So taking a step back now, we can ask ourselves, why are we dealing with convolution now as we're talking about Laplace analysis? So in order to answer that, let's assume that we have some f1 of t. And so let me say we have some f1 of t that gives us the Laplace transform gives us f1 of s. So f1 of s equals the Laplace transform of some f1 of t. And we also have some f2 of t, which is the Laplace transform of lowercase f2 of t. And so if you look on pages 696 and 697 in the textbook, you can see a proof for this equation I'm about to write, but it can be shown that our f1 of s times our f2 of s is equal to the Laplace transform of f1 of t convolved with f2 of t. And so what this means then is that convolution in our time domain corresponds to multiplication in our frequency domain. So convolution in time corresponds to multiplication in frequency. And so, of course, oftentimes multiplication is going to be a lot nicer to deal with than convolution, because remember, if we're doing this convolution analytically, we're going to have to do this integral equation. But there are some cases when we do want to work in the time domain. So let's come down here and say generally our multiplication is easier. But in some cases, our time domain is easier to work in. So in some cases, our time domain is preferable. And so a couple of those cases, for instance, would be, let's say our case 1 would be if our product f1 of s and f2 of s in our frequency domain is very complicated, then that can be difficult to inverse transform. So very complicated, it's then going to be hard to take our inverse Laplace transform. And so why is that relevant? Well, of course, if we come back up to our equation, we can see that this product and frequency domain is equal to the Laplace transform of the convolution. So we do have to, after taking this product, have to take the inverse Laplace transform in order to get our convolution F1 convolved with F2. So that's one case where it might be easier to work in the time domain. Another case is if we're working with experimental data. So maybe our F1 of t and our F2 of t are experimental data. So if we have experimental data for F1 and F2, maybe they don't have an explicit Laplace transform. So let's say maybe this doesn't have an explicit Laplace transform. And so, of course, so far when we've looked at our Laplace transforms, we've talked about these nice step functions, nice sine functions, but maybe we have something from our experimental data that is harder to define. Maybe it's something that varies over time like this. And so in this case, it's going to be easier to work in our time domain. And if we have something like this, we're actually going to want to do something called a graphical approach to our convolution. And so that's the topic that we're going to look at in our next video.